Hi everyone, I'm Radoslav and I'm going to be talking about PRIMECYC, which was a problem from 2 days ago, because 2 days ago it was the March lunchtime. And this problem was basically about some ad hoc observations, and after that it was pretty much like a brute force, which you had to optimize with some pre-compute. But overall, the interesting part of the problem was basically the ad hoc part, or like actually finding out the observations. So yeah, this video tutorial will be quite short because the problem kind of involves just some observations. So without further ado, I'm just going to go to the problem statement. So the problem was called PRIMECYC, and basically in it you were given a full binary tree of height n. Know that the tree is of quite small height, but this doesn't really mean that it has like few nodes. It basically has like 2 to the power of n minus 1 nodes, because it's like a full binary tree. And yeah, we are basically like given like this tree, and also every vertex has a value written on it, which is given by AI. So we define a prime full cycle as basically a set of nodes where we have like k nodes, and also we want k to be prime. So in a way, like we choose a prime number of nodes, and it doesn't really matter where those nodes appear. It's just like necessarily for them to be like k, where k is prime. And also the constraint we want them to satisfy is based on their values, so like the AI values. And what we want is that in a way the cycle has some ordering for it. So we want for every two adjacent elements to have the same reminder of their GCD. So formally, like we want the GCD, or like the greatest common divisor, of every 2 adjacent numbers to be similar when we consider it modulo k, where k is again the length of the group. This is like a very specific constraint when you think about it, but in a bit we are actually gonna see what it actually means. And yeah, and now like this is the definition of a prime full cycle, and we are also given a definition of height, which is basically the normal definition of a height in a tree. It's the number of nodes from the root to basically a specific vertex. And also we define the height of vertex 1, like the root, because 1 is always the root of a binary search tree, a binary tree given in this form. So we define the height of 1 to be also 1. So in a way, like we also include the node we are looking at. And yeah, I mean, now the beauty of a prime full cycle, so this definition with some set of nodes, which aren't necessarily adjacent, it's basically defined as the sum of heights of all nodes. So in a way, it's basically the sum of the depths, or like the heights. So now, in this problem, we are given those definitions so far, and we want to answer queries, where every query is just defined by a single node x, and what we do, we just consider the subtree from this node, like just all the nodes in the subtree of x. And what we want is to actually consider all prime full cycles that have nodes only in this subtree, so you can ignore all other vertices. And we are interested in the smallest possible value of a prime full cycle, so like this definition, which yeah, I mentioned. And yeah, the value is, again, I should remind you, it's basically the sum of the heights. And yeah, also, if there is no such cycle, we print -1, but we are going to see that almost always we have such a cycle. So yeah, I mean, that's pretty much the problem statement. You can check out the constraints. There are only 2 subtasks, and they were different based on the number of queries. And basically, you always have quite a lot of nodes. And yeah, I mean, you can see that the values are relatively large. Q, which was the number of queries, is up to 10 to the 5, n is to 20, which means that overall we have around 1 million nodes. But yeah, that's pretty much the problem statement. I guess let's just go to the solution. And yeah, basically how the solution would go is, you can kind of see a spoiler here already, but first of all, we have the problem statement, which I already discussed. Then now I'm going to talk basically about some observations. And those observations basically lead to the fact that we always will choose exactly 3 nodes, which is pretty much the most important observation in this problem. And after that, it's pretty much brute force. So yeah, let's go to the observations and actually the intuition in the problem. So yeah, the main observation is that in every set of 7 nodes, like just choose whichever 7 nodes or like 7 numbers, there are definitely there are definitely exactly 3 of them. Maybe, I mean, yeah, let me state it in another way. You can always select 3 numbers so that they form a valid cycle, like a primeful cycle. Note that 3 is a valid number because it's like prime. So yeah, you can always choose 3 numbers. And yeah, I mean, basically, the full proof will be in the editorial, and now here I'm gonna, like, basically the text editorial, and here I'm gonna just outline the main idea of how to actually get this observation. Know that we have 7 nodes. So the first thing we need to note is that if we have at least 3 numbers that are divisible by 3, basically in our set, then you can notice that we can literally just choose those 3 numbers. Maybe there are more, but so if they're like more than 3 numbers divisible by 3, we just like choose any 3 of them. And you can notice that the GCD of each pair of them is actually divisible by 3, because all of them are divisible by 3. Therefore, all of the GCDs will be equal to 0. And yeah, we're basically done, as we can just choose those 3 numbers. So in a way, like, we can assume that there are just 2 numbers that are divisible by 3. And let's say that we are going to remove one of them and just stay with the other 6 numbers. This removal is important for the next part, because like in our construction we are going to use, we only need 6 nodes for it to work. And also, now I'm going to basically go to the construction, which is kind of graph based. So yeah, consider we have a graph where the vertices are actually our numbers and the edges represent the GCDs. So in a way, like, you have a graph where every vertex is some node and every edge is labeled by the GCD. So we are basically going to color the edges, and we are going to say that the red edges are when the GCD is 1, and they're blue if the GCD is basically 2. And let's say that we just pick some arbitrary vertex. If we have like one vertex that is divisible by 0, so like, as you can remember, here we kind of removed just one of the vertices that are divisible by 3. So like because our construction needs 6 numbers, if we have like one number that's divisible by 6, so one number that's divisible by 3, we're going to use it as the initial number. This isn't really important, but like for simplicity, we can just assume it. And yeah, now we color the edges based on their GCD. So in a way, like, we have red edges and blue edges. And to remind you, what we actually want in our problem is to basically select 3, maybe not 3, but like more edges, such that the color of all the colors are the same. Now we're basically proving that in those 6 vertices, we'll always have at least 3, such that the colors of all edges in them are the same. So in a way, like, you are going to have a triangle which is of the same color. And one of the main observations here is that we can actually use the pigeonhole principle. And what it basically says, this is like kind of a generalization of it, but we know that there will be at least one color that will appear at least 3 times if we just choose an arbitrary vertex and like look at all edges from it. Then there will always going to be like at least, I mean, one of the colors will always appear like at least 3 times, because you only have 2 colors and there are like 5 edges. So yeah, one of the colors will appear at least 3 times. And let's say this will be the blue color, just for simplicity. I mean, it might as well could have been like the red one, but without loss of generality, we can assume that it's the blue one. And now let's consider, so I mean, you have those blue edges, and let's look at the vertices which are connected with blue edges. So now let's also add all edges between them. So I mean, in this example, we have 3 edges, and those edges, I'm gonna call them the purple edges. And you basically have like a purple edge between each pair of those nodes which are connected with a blue edge. So ideally, what we want is to have like at least one of those purple edges being blue, because if we have at least one of those purple edges blue, then we have like this triangle, which is basically using the top vertex, like the initial one, 2 of the vertices that are connected with, and to like 2 of the vertices which are connected to it with a blue edge. And yeah, if like we had, for example, this edge being blue, then we could have just used this triangle. And yeah, I mean, the proof pretty much goes in a quite easy way. We have like basically just 2 cases. The first case is that all of the purple edges are actually red. So I mean, all of those edges are red. In which case, we can actually just choose all those 3 edges, all those 3 vertices. Because of the pigeonhole principle, we know that we have at least 3 such vertices. And yeah, I mean, we can basically just choose all of them. And we have proved that in those 7 vertices, we have at least one triplet that actually has, satisfies our constraint. And now, like, the second case is actually, we know that not all of those purple edges are, not all of them are red. So this means that at least one of them is blue, which means that we actually have this constriction I described some time ago, which was, we basically like, you choose the top vertex and 2 of those. Because like this edge is blue and you can, yeah, basically choose the top vertex and 2 of those. And yeah, I mean, you can either have like all of the purple edges red, or at least one of them won't be red. So it will be blue, which means that in both cases we actually found a construction that shows that we always have a triplet that is satisfying. So this means that in every set of 7 nodes there are 3 that form a valid cycle. And yeah, I mean, we just proved this. The proof is kind of like graph-based and it's pretty neat. It wasn't so easy to find it based on like the number of people who solved the problem, but I think it's quite interesting and it could be adapted to some other problems, so you can have it in mind. So yeah, this was like one of the main observations in this problem. And after that, we're gonna basically show that we can always choose 3 nodes. And this is based because we should remember that k is needed to be prime, so we can't really choose k equal to 4 or like a smaller k, because k equal to 3 is the smallest case. And yeah, for k equal to 5, you can notice that the sum of heights will always be greater. And yeah, I mean, this is the way we actually prove that it's always optimal to choose 3 nodes, because I mean, all other constructions, like the smallest k is 5, and for 5, we always, I mean, the lower bound for 5 is actually greater than the upper bound we can get from 3 nodes. So yeah, I mean, the upper bound for 3 nodes, because this is also important here, is, so consider some arbitrary x and the query. So we have like, the x is the root of the query, and let's consider the binary search tree, but only on the first 3 levels. So I mean, basically x and the 2 levels below it. And we know that the height of x, let's say, is h. So this means that in those, basically, I mean, we know that there are 7 nodes on the first 3 levels. And we know that our construction actually requires 7 nodes. So this basically means that the max height, this basically means that we actually have a construction that gives us an answer, which is the upper bound for the answer. It's like 3h plus 6, because we know that the maximum height here would be h plus 2, because yeah, we have like this bottom, the bottom level, and all nodes there are h plus 2. And we know that in our construction we can choose always 3 nodes. So I mean, this like trivially you can get that the answer is definitely less than or equal than 3h plus 6. So yeah, I mean, this way we are pretty much done with the problem, and we kind of just do brute force. So the main idea is that let's consider nodes that are on depth just less than or equal than 5 from the root. So in other words, when we have some query with some root, we are just going to consider the first 5 levels. Technically 6 if you include the root. And this is mainly because you can notice that we need the answer to, if we have something, a node that's on height greater than 6, then the answer we are going to get is definitely greater than the upper bound we have. So it doesn't really make sense to actually consider search cases. So that's why we can also only consider the nodes on depth less than or equal than 5. And yeah, you can notice that obviously because the tree is binary, you have 2 to the power of 6 minus 1, which is 63 such nodes. But unfortunately, this still leads us to a quite slow solution, because I mean, technically this is slightly less, but I mean, we have quite a lot of triplets because we have 63 nodes and we need to choose 3 of them. I mean, this is actually 63 choose 3 and not 63 to the power of 3, but those are approximately equal. So not approximately equal, but like in big notation, they are kind of equal. And both of them will yield quite a lot of triplets. So we kind of need to optimize our brute force, because we can't really perform all such triplets, go through all such triplets for every query. And yeah, but we need to remember that we actually have such an upper bound of 3h plus 6, so we can initially just set our answer to this number. Of course, if there is a solution, but we kind of prove that we always have a solution when the tree has depths less than, when the node isn't on the last 2 layers. So this kind of means that we only need to technically check triplets that potentially have sum of heights less than 3h plus 6. And it turns out that they're actually always less than 200 such triplets. And this is, I mean, to prove this, you kind of need to consider the different cases, because, I mean, you can basically enumerate all cases as the depth is quite small. But this is slightly annoying to implement, so probably the best way to implement the solution would be to just pre-compute all tuples in the beginning, because, I mean, you can consider just as if you have a very large tree, which kind of, I mean, yeah, the main idea is to kind of like pre-compute in the beginning, and after that you can basically just, for every node, kind of iterate through just the pairs that matter. So this is like one way to implement it. Another way to implement is, as I said, they're like, because, I mean, the depth is quite small, so you can kind of enumerate the different cases. For example, you can't really have more than one node on depth 5, then you can't really have more than one node on depth 4, and also like for depth 3, you can have at most 2 nodes. So this way you actually get quite few possible triplets, because, I mean, for the other nodes, you only have a choice out of 7 nodes, and yeah, clearly from 7 nodes, if you can choose 2, this is like not a lot of possibilities. It's around, yeah, it's 7 multiplied by 6 over 2, which is 21. So in a way, like in those 4 cases I just described, there are at most 21 possible ways to actually choose the other nodes. So yeah, I mean, you can notice that there are like very few triplets you actually need to consider. You don't really need to go through all 63 cubed triplets. But yeah, I mean, this is pretty much the solution. You kind of prove this initial observation, and after that it's just a brute force. So yeah, again, like pretty much the other way to do it is kind of pre-compute, and after that just iterate through all pre-computed things, which are quite few for every query. And yeah, I mean, that's pretty much it. So yeah, I guess thanks for watching.